welcome to my talk. So I will talk about closures in Scala and how to avoid various safety hazards when you use closures in concurrent and distributed settings, mostly. Before I start, just a few words about my own background. So I'm a faculty member at KTH, the Royal Institute of Technology in Stockholm, Sweden. And before I joined KTH, I was actually a member of the Scala team for about 9 years. And some of that time I spent at TypeSafe, which is now called Lightbend. So you might know Lightbend from, the development of various frameworks for distributed and serverless computing. And so in 2019, we were actually humbled to receive, let's say, the highest academic recognition for programming languages software for the development of Scala. And my own focus has been distributed and concurrent programming. So, for example, I created Scala Actors, which was sort of the first widely used actor library for Scala. And that was actually used in production at Twitter and BBC and some others. And then I've been involved with various efforts for concurrency in Scala, so like Scala's futures and also Scala async. But today, I want to talk about closures, right? Because closures are pretty essential for much of what we do nowadays. And but there's a lot of things that can go wrong if we use closures in a concurrent or distributed setting. So I'm going to talk about some of these things. So that should be fun. And then I'm going to talk about how to actually write safer code that uses closures. And sort of in the second part of my talk, I'm going to talk about a new library for Scala called Spores 3 that makes it, let's say, safer and also more flexible to use closures in Scala. And I'm going to sort of dive into some part of the implementation, in particular regarding serialization. So let's dive in. So first, what's a closure? You've probably all used closures before, so I don't need to dwell too much on it, but I want to use this opportunity to actually remind ourselves about the sort of first and original definition of what a closure is, which is quite nice. So here in this example, right, we're just creating a list of numbers, and we have this integer threshold, and then we're using this filter combinator to filter out all the numbers that are below the threshold. And of course, this part in blue here is a closure in Scala, and so this is Scala code. And sort of for this definition of what a closure is, I'm going to, of course, assume lexical scoping. So I don't care about dynamic name binding in this talk. So everything is assumed to be lexically scoped, right? And so this anonymous function here in blue, right? It kind of refers to this threshold variable in its lexical context, right? And this is of course fine because that's the whole point of closures, that we're able to do that. And so now with this we can actually look at the original definition of what a closure is, which is attributed to the late Peter Landin, who was professor at Queen Mary University. And according to his definition, a closure, right, is an anonymous function that has some called open bindings. Okay, these are essentially the free variables of the closure, and these open bindings have been closed by the lexical environment. Okay, so that's why it's called a closure, because the closure closes the open bindings. Why is this an open binding? Well, because here we only have a single binder for the num parameter, right? Threshold is not bound within this anonymous function. Instead, we close this open binding using the lexical context, where we essentially look up, what's here, defined earlier in the surrounding scope, and then we essentially copy that value into the environment of the closure, so that when the closure executes, we can actually access the value, right? So now we all know where this word closure comes from. And of course, closures are pretty essential to a lot of tasks. For example, data processing. So here is an example using Apache Spark, which you may have used yourself, right? So here we can essentially create distributed data sets. In this case, just from a simple text file. But then we can use combinators like map and reduce, to transform and reduce these distributed data sets, right? So using map, for example, we pass a closure that is used to transform a data set of lines into a data set of integers, which are the numbers of words on each line, right? And then we use reduce to essentially compute the maximum number of words on any line in that file, right? And these two blue things are, again, closures, right? So the code is just completely based on closures. But of course, we also use closures in the setting of concurrency, right? So this is now using Java for a change, right? Where we basically we're given a list of customers, and we want to, concurrently compute the average age of this list of customers. And we essentially do that by creating a task that we ship to a thread pool for execution, right? And in this case, we define this closure in blue, right? And this closure, takes this list of customers, and it uses the Java Stream API to, transform this first to an int stream using this getAge method, and then, it computes the average and returns that as a double, okay? And then, this closure is converted to a SAM type callable, and that task is then submitted to an executor, which is essentially a thread pool that, asynchronously computes or executes the closure, right? But it immediately returns a future that we can use to, access the result when it comes in. Okay, so this is pretty common. Of course, if you use futures in Scala, you also use closures a lot of times. So this is, again, quite common. Now, of course, the issue is that there's lots of ways in which things can go wrong if you use closures in these settings. So let's have a look at an example, right? So here, again, we're using Spark, where we take this toy array of integers, and we turn this into, again, a distributed data set called RDD in Spark, right? It doesn't really matter the details, but we turn this into this distributed data set, which in general is distributed across a number of executors, so we can represent data that doesn't fit into the memory of a single machine, right? And okay, we have this sort of trivial transform method that we're now going to use when we use the map combinator on this distributed data set. And basically, we want to transform the data set such that each element is mapped to the result of transform of elem, right? Fine, we just increment each integer by 1. And then, of course, at the end, we just collect everything on the driver node and print each element. Now, this looks quite simple, right? That's probably one of the simplest programs you can write using Spark, right? But if you do that, turns out you actually get an exception which says task not serializable. That's a pity. Fortunately, you get quite a bit more information nowadays, but I'm not going to show that just for fun. But essentially, to understand this error, we need to look at this closure in blue, right? Again, it's a very simple closure. But why it's sort of tricky is because we use it, for this map method on distributed data sets. And like I mentioned, distributed data set, right, is sort of spread across a number of worker or executor nodes. To run map basically requires that this closure is serialized and sent to each of these workers. Okay, so we have to be able to serialize this closure. Okay, well, if you look at this closure, it uses, this transform method. That seems reasonable. But of course, transform is just short for this dot transform, right? So actually, what this closure does is it captures the this reference, okay? Now, if a closure captures something, right, and we want to serialize the closure, we have to serialize everything that's captured. So we have to serialize the this reference. Now, what's the type of this? Well, it's a Spark example, right? This enclosing class. But that's actually a class type that's not serializable, okay? And that's actually why we get this exception, right? So we kind of accidentally capture something that maybe we're not aware of that's not serializable. Right, so basically what this means is that, we cannot just use closures as we're used to in a local or a sequential setting when we go to distribution, right? It's a bit of a safety risk. And like I showed, we can have runtime exceptions, like not serializable exceptions on the JVM. And now I could also think about, well, what about concurrency, right? And if you just revisit this earlier example that I showed you, here we actually have a closure that captures this customer's parameter, right? And well, it turns out, as you probably all know, lists in Java are actually mutable, at least the default ones, right? And so that means that this customer's list might actually be mutated concurrently, right? Because whoever calls this average age async method could pass in a list that is mutated concurrently with while this closure is being executed. So here we actually have a risk for data races. So also, concurrency can be tricky, right? Because we can easily get data races if we execute closures on concurrent threads. And these closures refer to shared mutable objects. Anything else? Well, there are, of course, a lot of scenarios that we want to use closures in. Like, for example, most applications or many applications have a front end maybe that runs on a JavaScript engine and a back end running on a JVM. So, in some cases you might want to actually send a closure from the front end to the back end, right? Just like in Spark, you send closures, from the driver to all the executors. So this is a perfectly reasonable thing to try to do. But if you want to do that, well, you actually need a portable serialization scheme, right? You need to be able to serialize something on the JavaScript side that you can actually deserialize on the JVM side. And well, good luck doing that with the closure, right? That's just simply not possible with closures out of the box. So, yeah, if we look back at what I showed you, right? These safety issues, they actually come from this unrestricted variable capture, right? It's completely unrestricted what we're allowed to do. So, right, in the case of concurrency, nobody prevents us from capturing mutable shared objects, right? Or in the case of distribution, we can easily capture objects that are not serializable or that just don't mesh well with distribution. So we can think of, potential remedies, right, where we could say, well, how about we restrict the types of these captured variables, right? So we could kind of try to impose requirements that, okay, you're only permitted to capture types that are known to be serializable. Or we could also think of, providing or using different modes for capture, right? Capturing modes. So instead of just copying a reference to a mutable object into the closure, we might think of maybe first deeply cloning a mutable object before we copy a reference to that into the closure, right? So that the closure has a well-defined, snapshot of the objects that it's going to operate on. So there are, at least these kinds of things we can think about. Yeah, so essentially, if you want to spot unsafe code, we of course have to, look at the environment of the closures, right? So all these, it's captured variables. And there's of course a bunch of, let's say, code smells, right? So capturing a var, which is in Scala a reassignable variable, that's usually, probably not a good thing to do, especially not if we're using concurrency or distribution. So especially if this thing is reassigned in the body of the closure. Now in Java, you don't have this issue because captured variables actually must be final. But as we've seen, this does not prevent, these kind of bugs that I showed you before in this, where we used a future, or a callable that executed a closure concurrently. Then, we should think of, we should check the types of what we're capturing. So mutable types can be an issue. And of course, if we do distribution, there's a number of types that just don't mesh well with that. Perhaps because they're not serializable, or because, sorry about that, or because, they're just not, they cannot be used in a distributed setting because remote executors might not be able to access whatever the closure needs, okay? And so the question is like, how can we write safer code? And of course, the basics first, right? I mean, first of all, we need to be able to spot, what are we actually capturing. So our closures should obviously not be too big. I mean, this applies to any, let's say, method, but probably especially for, applies to closures. And also, we should not capture too many variables, I suppose. So if you, capture 10 variables, it's probably not a good idea. But then, we have to sort of look at the types of captured variables. We should, of course, let's say, prefer immutable types. Immutable types are probably, in general, preferable. I'm probably preaching to the choir here. But in the case of closures, this is, of course, especially interesting because, closures are created and executed at different points in time. So immutable types make reasoning, much simpler. And then we should think about any required properties, right, of the captured types. Do they need to be concurrency safe, or serializable, and so forth. But in general, what we have to check here is actually also the creation of closures, right? What happens when you create a closure? So essentially, right, the question is, what's the logical snapshot of the memory that the closure should be initialized with, right? Because the closure only sees, the logical snapshot that is represented by the things that we're capturing. So for example, is it really sufficient that we initialize the environment with the copy of a reference? Or maybe we have to, clone a mutable object first, right? So these are sort of important questions. And then, of course, the semantics of the closure itself, it's pretty obvious that we need to look at that. But in a concurrent setting or distributed setting, of course, we need to see, like, do we need something like a transactional semantics, for the application of the closure, right? Is it sort of an atomic update of the state of something, and so on. So, excuse me. So these questions are not completely trivial, and that's why I want to now introduce a new Scala library, which is called Spores 3, that tries to make it a bit easier to create closure using code that's actually can be very safe based on type checking and is also quite flexible. So what is the goal, right? The goal is essentially to provide an abstraction that we can use actually as a drop-in replacement for closures, almost, right? And that, like I said, is sort of much safer in especially concurrent and distributed settings, and has some nice perks compared to regular closures, okay? So what we want to require, right, is, first of all, we want to be able to, constrain the environment of our closure-like abstraction, right? So somehow using types, we want to express constraints on the captured variables. Then we want to support serialization based on type classes. So I'm not going to explain what this means, really, type classes. If you've used it before, in fact, if you used Scala, chances are very high that you've actually used type classes. But essentially, it's a way to look up at compile time the serialization logic that's required to serialize the given types, okay? And the advantage of that is that it's very efficient, and it's also safe because, we statically check whether a serializer is available, okay? And plus, we can make it portable, which is another plus. And in fact, the whole implementation of this library is designed to be completely portable from the beginning, right? So Scala now has, 3 different backends, JVM, JavaScript, and native. Okay, the native backend is still sort of beta, but we want to have a portable solution. And also the implementation is designed to be, relatively simple and quite robust because, we try to kind of minimize the use of macros, right? So macros is code that runs at compile time that can also generate code and all kinds of stuff. So this can easily, the complexity can easily sort of go out of hand. And so what's the idea? The idea is, it's called Spores, okay? And this is actually not a new idea. In fact, Spores have been introduced a few years ago in a research paper by Heather Miller, Martin Odersky, and yours truly, right? And so it's not a new thing. And what a spore is essentially a special kind of closure where the environment is explicit, okay? So it's not sort of implicit that you just refer to something you want to use, but you actually have to kind of make an effort to, include something in the environment of a spore. And we also track the type of the environment in the type of the spore, okay, using type refinements in Scala. And this is quite powerful because we can actually express constraints on the environment using types. And that's, of course, good because, Scala has a quite expressive type system, so we're able to express various constraints. I'm going to show you some examples. And then finally, of course, we need to be able to, execute some operations on our Spores environment, for example, to serialize it or to duplicate a spore. Right, so then what's new in Spores 3, right? And that's essentially a completely new implementation of Spores for Scala 3. And it tries to address some limitations that the original Spores for Scala 2 had. So, okay, one aspect is that, we try to limit the use of macros to essentially compile time checks, okay? So we're not doing a lot of code generation because that, caused some issues with the earlier implementation. And like I mentioned, Spores 3 is designed to be portable from the beginning. Is the audio still? Yeah. In contrast to Spores for Scala 2, okay? So there was some experimental efforts to, support Spores on JavaScript, but that was never really released. But perhaps what's most interesting is that Spores 3 actually has a quite interesting, I think, approach to serialization based on type classes, and that's cool because it's, first of all, it's flexible. So we can integrate this with various serialization libraries, of which there are plenty, as you know. But it's also portable, and we can sort of enforce serializability statically. So it's quite safe. So let me give you a quick overview of Spores. So if you want to create a spore without an environment, that's quite simple, right? So we can simply pass a function literal to the spore factory. And in this case, we actually have a macro that checks that this function literal does not capture anything, okay? So this is, if you would try to capture something, this would be rejected at compile time, okay? So this is a very well-behaved, spore, basically. And the type of such a simple spore is basically, spore from int to int, so parameter type int, result type int, and then it has this type refinement, where we basically have this type member env, which is equal to nothing. What does that mean? Well, so this spore doesn't capture anything, right? So the environment, there is no environment, and nothing is the bottom type in Scala, so it's a subtype of all other types. And in fact, there's no variable that has type nothing. And so that's very fitting, because if you would try to read the environment of that spore, there's nothing that we could give there, right? So the only thing we can do is throw an exception, right? And so the type nothing makes a lot of sense here. Spore types are also subtypes of the corresponding function types, right? So spore t, r extends t arrow r. And of course, it's contravariant in the parameter type and covariant in the return type. And we have this type member. And here in this definition, it's abstract, right? Because it's sort of only set when we create a concrete spore. And of course, this thing needs to be sealed because for this to be safe, we cannot allow user code to extend that trait. Right, so let's look at some more interesting things. It's like spores with environments, right? And in this case, we need to, again, because the environment is explicit, we need to kind of explicitly initialize the environment. So let's say we have this variable str that should be captured by the spore so that it can be used within the spore. So to be able to do that, we need to pass it as an argument to the spore factory. And then, the body of the spore now has this additional parameter env, okay, you can call it whatever you want, but the first parameter is the environment of the spore, so that in the body we can use it, right? Okay, and now if you do that, this spore has a different type, right? It's spore int to int, but this type member is equal to string, right? Because the environment is, consists of a single string. All right, so now the first question you might have is, well, why do we really want to use this extra parameter for the environment? That seems rather, clunky. And well, sure, user code needs another parameter, but it's also quite nice because we can actually use pattern matching when we access the environment, right? So let's say you want to capture two things. The way it works is we pass these, again, we have to initialize the environment explicitly, right? So we pass them in as a tuple, and then we immediately use pattern matching to, destructure the environment, okay? So this is actually quite nice if we, if the environment consists of multiple variables, okay? And this is possible because, the environment is the first parameter, so we can easily use pattern matching there. Okay, now, but what's more interesting is actually these type-based constraints. So essentially, since we have this type member, we can actually express some constraints on the environment. And for this, we would typically use context parameters or in Scala 2, they were called implicit parameters, right? So for example, let's say we have a method that takes a spore and it wants to constrain the environment so that we can only capture thread-safe types, right? So here's an example. So let's say we have this future method that takes a spore, which is essentially a thunk, right? So it takes unit and returns t. And well, this method is supposed to, spawn a concurrent computation that executes the spore and immediately returns a future of t. But now, of course, we want to say that, well, for safety, right, whatever the environment of the spore is, it should be thread safe, right? It should not access shared mutable objects, right? No, should be thread safe. And so we can use a context parameter to constrain the environment type, right? So we can actually select this env type member from the spore S to say, well, we need to have an instance of this type class, thread safe, okay, for this type s.env, right? And you can imagine, so thread safe is not actually part of the Scala standard library, but you can imagine that, this is a type class that we can define where essentially there's an instance for all the thread safe types, like all the primitives, all the like immutable types, and also things like concurrent hash maps and so on, right? These could all have instances of that type class, right? And so if you would capture one of these things, that would be accepted. But if there's no instance of that type class at compile time, right, then calling this method would be disallowed, right? So we could not call this method with such a spore, right? And so this is really quite powerful. So this lets us express things a bit similar to sendable closures in Swift, for instance, right? And I'm going to use the same trick actually later on when we talk about safe serialization, right? So yeah, let's talk about serialization, right? Because I already mentioned what we want to have is kind of a flexible way to serialize closures. So we want to be able to integrate with various frameworks because, as you know, there are many of those, right? So yeah, we need to integrate with different ones. We also want to have a portable way so that we can support what I mentioned earlier, right? This scenario where we can send closures between machines running on different backends, essentially. And also, we want things to be safe. So, whether a spore is serializable or not should be determined statically, right? So that we avoid these issues we saw earlier with in Spark, for instance. Okay. Now there are some assumptions we need. First, serialization is supposed to be used mainly for communication between remote machines. So we're not going to use it for data persistence, let's say. And also, one assumption is that every node is actually running the same code. This might sound like a strict requirement, but turns out, these frameworks like Apache Spark and Flink and so they actually have that requirement as well. So this is not such a big deal in the end. So this is a quite common assumption. Then finally, we don't want to transmit any bytecode or source code for security. Right, what's the approach? Well, instead of serializing the code, we don't want to send code, we serialize a unique identifier that lets us instantiate the implementation of that spore and, of course, the environment of the spore. So in practice, what we do is we create a named spore builder that lets us instantiate the implementation of a spore, and then we can serialize the fully qualified name of that builder. So here's an example. So here we create a builder, spore builder, which has the types of the environment and of parameter and return type, and it has the implementation of the spore, right? And then we can, using this builder, we can create a serializable representation called spore data, which takes a spore builder and the environment of the spore, okay? And then we can actually serialize this spore data as usual, right? In this case, using micropickle. Yeah, nothing special here. And then we might get out some JSON like that, where we have the fully qualified name of the builder and the environment. Right, but what I want to talk about is actually this safe serialization, right? So let's say we want to write a method send off that's supposed to serialize a spore and send it, across the network. How do we do that? And how do we ensure the safety of that? Well, what we can do is use the spore data, which is a serializable representation, which has exactly the same structure as the spore type. So it has this type member for the environment. And in this case, we actually leave the environment type polymorphic, right? We abstract from that. And S is just a type parameter which has that spore data as its upper bound. And this is just as a shorthand. And then, this is the parameters spore data of type S. And then we can again use a context parameter to enforce that there's a type class instance for type S. Called readWriter, which is essentially the serializer for that type. Okay. In Scala, we can also abbreviate this with so-called context bound, okay, which says that for this type S, we need to have an instance of that type class. Okay. And this actually now means it's checked at compile time whether the spore is serializable because its environment is serializable. I'm going to skip over that because I see I'm running a bit late here in time. So just a few words about how we implement serialization. So like I mentioned, we have the spore builder that we use to find the implementation of the spore. And what's really cool is actually how we look up the serializer and deserializer. And we do that when the builder is constructed. So the constructor of the builder, right, takes, of course, these type arguments, but also takes the body of the spore, which is here, right? And but it also has this context parameter. So at compile time, this is resolved, right? So we look up the readWriter for type E, and then it's available, in the body of the builder. And this is really awesome because at the point when we actually want to create a spore, like in memory, but we still have the environment in serialized form, in this case as a string, right? We can actually deserialize the environment because we have the readWriter in scope for type E. So we can actually deserialize the environment like using a type-specific deserializer, okay? So I think this is really cool. Yeah, then finally, the spore data, actually what we do here is we actually check that the builder is a top-level singleton object that has a fully qualified name that we can look up on different nodes in our network. And we also look up the fully qualified name like at compile time, so we don't need to use reflection for that. And then we can, of course, serialize that. Yeah, I'm just going to go a bit fast here. So the implementation is open source under Apache 2 license. Like I said, Scala JVM and Scala JS is supported, and we plan to support Scala native very soon now, right? And yeah, integration with uPickle is sort of provided out of the box, and we plan to do more. Yeah, summary. So like I said, distribution and concurrency kind of pose some safety risks when we use closures. If you want to do things in a safer way, we have to consider captured variables, their types, and the capturing semantics. And this is made easier using Spores 3, right, which is essentially a new implementation of the Spores idea, but for Scala 3. And yeah, Spores have an explicit environment that we track using type refinements. We can express type-based constraints to make things statically safe. And we have a way to serialize Spores that's quite flexible, portable, and also statically safe. With this, thanks very much. And unfortunately, we're sort of out of time. So if you have questions, just find me afterwards. Yeah, thanks again.